Welcome, everyone. Thank you for joining us for today's webinar. My name is Ismail Benayoun, and I'm the US West Technical Director at Altair. Today, we are kicking off our webinar series on how to accelerate your electronics device design. Just a little housekeeping before we get started. If you have any questions during the presentation, please type them into the question box in your GoToWebinar control panel, and I will bring them up during the presentation, and we will also have a dedicated time for questions at the end of the session. So this webinar series is composed actually of two major tracks. And the first one is the mechanical series, which will cover the broad scope of product design, from concept evaluation to manufacturing, going through some of the most complex simulation techniques and use cases. We will demonstrate how Altair Multiphysics platforms offers the most comprehensive simulation and optimization solution in the market. The second track is the electromagnetic series. Our high-frequency electromagnetic expert will cover the topics of PCB design and verification up to manufacturing. They will also cover the antenna design process, their placement, the performance evaluation and optimization. And at last, they will show how to solve coexistence and interference issues between connected products. All this using Altair's EDA and EM simulation platform. Both these series will cover examples and models from various types. In fact, we will demonstrate the different solutions using various electronic devices, such as smart speakers, hand controllers, or Bluetooth mouse. We will cover the various needs in the product development cycle, meaning from the concept to the reality, with the analysis of components, sub-assemblies, systems, and systems of systems. In few words, what we would like to share with you is how Altair is helping and helps companies reduce time to market by enabling advanced multiphysics simulation and optimization, machine learning, all leveraging one simulation platform. Today's webinar is all about speed and accuracy. How dozens of designs can be analyzed on the fly to eliminate guesswork and provide valuable inputs. And this is only possible because of the simulation time that is reduced to seconds or minutes. Too good to be true? Well, this is a technology that is adopted by hundreds of organizations around the globe already. Today, I picked two examples. The first one from one of the largest automotive OEM group, Renault-Nissan-Mitsubishi Alliance, for whom Altair means efficiency. Indeed, Altair has always been a key player in shortening the virtual product development cycle. Another example here is LG Electronics. Using Altair simulation, they are slashing the time required for drop test simulation from days to hours. So you've probably heard about Altair before, and if not, please allow me to take 2 minutes to tell you a little bit about us. Our vision guides our actions. We do our best to develop the cutting-edge technology that can transform customer decision-making with simulation, data analytics, and high-performance computing. With more than 11,000 customers around the globe, my 3,000 colleagues and I are located all over the world, developing and supporting more than 150 advanced software products. These products are the fundamentals of the broad solutions portfolio we are offering to you, from design and modeling and visualizations to multiphysics solvers to data analytics and high-performance cloud computing. While our roots are in the automotive industry, when founded 35 years ago, we today develop solutions that are designed to deliver excellence across various industries. Here you can see some of our customers in each of the verticals. Now, without further ado, we will start today's topic, and I will turn the time over to Leo Zhang. So Leo is our presenter today. He is Altair's Electronics Technical Account Manager. He's been an Altair application engineer for the past 5 years. Prior to that, he spent 4 years as a structural analyst in the aerospace industry. He's almost a globetrotter. As he moved from LA to Boston, then to Sunnyvale, California, where he is based right now. And he's a true animal lover. He just got a dog due to COVID and being bored. So with this, Leo, the floor is yours. And let me make you presenter here.
Sure. All right. You guys can see my screen, right?
Yes. Yes.
Okay, cool. Yeah, thanks everyone for attending. Like Ismail introduced, my name is Leo and I'm an application engineer at Altair. Today we'll be talking about simulation-based methods for rapidly evaluating the structural performance of complex electronics assemblies and how to expedite that design process. So let me go over the agenda of what we'll cover today. So we'll be covering the difficulties and challenges of the consumer electronics industry. Then we'll demonstrate a rapid design evaluation workflow and pause for a Q&A session, then move on to a design generation workflow and wrap up with another Q&A session. So to start off, let me talk about the difficulties of product design in the consumer electronics industry. Probably one of the most difficult things about product design in the consumer electronics industry is the sheer number of parts in an electronics assembly. If we look at a phone, tablet, laptop, etc., there's hundreds of components in there, and it becomes difficult to gauge the overall structural performance of an assembly due to difficulty in part management, tedious repetition of tasks, and just complexity. Another challenge is the time to market. So the consumer electronics industry is a very competitive field, and oftentimes competitors are racing against each other to reach the market faster. So engineers are required to make rapid design changes and give feedback on an almost next day or even same day basis. Lastly, product design itself contains many engineering disciplines. We see different engineering teams across different industries. We have design engineers, we have analysis engineers, manufacturing engineers, etc. A lot of the work is siloed, and oftentimes designs will change and need validations from other teams to move on. So with all these difficulties in mind, let's look at several ways that we can address these hurdles. The first way is coming to the right design as early as possible. Again, the product design process involves iterations across many teams, particularly the analyst and the designer. If simulation was incorporated as early as possible into the design phase, that would lead to an informed design. We also need answers to be fast, so there's a need for tools that can rapidly deliver results at a faster pace than the status quo of an analyst taking multiple days to set up a run. Next, the processor tool has to be accessible and easy to use so that engineers across multiple teams with different backgrounds can adopt and pick up a tool without a steep learning curve. So with that in mind, let me discuss the traditional workflow for how engineers do simulation nowadays, just to illustrate some of the hurdles that can lead to longer lead times. So for anyone familiar with simulation, we know there's a couple different hurdles when it comes to utilizing simulation in a fast-paced environment. The typical process is that when an analyst wants to start simulating, they first have to import the CAD from his or her designer and start prepping it for mesh. Things that designers wouldn't otherwise care about, such as duplicate surfaces or threads on a screw, are important to the analyst to get rid of because they could cause bad elements or disconnected elements, which would give bad results. So once the analyst cleans up the CAD, they actually then have to start meshing. So this is where exercising judgment and picking element types and how to proceed with meshing the CAD, as well as assembling their own hierarchy. The analyst also needs to clean up the mesh itself, since perfect CAD doesn't necessarily mean perfect mesh. Next, the load case has to be set up. So the boundary conditions, forces, etc. need to be applied, as well as material assignments. And next, the analyst can finally start running the analysis. So this would basically let the solver run in the background and actually solve the equations involved in this analysis. At this point, the analyst can finally start post-processing the results and looking at things like local deformations and stresses. And finally, they compile these results into a report and make sure the results make engineering sense, given the assumptions they make during the load case setup and whatnot. So with any change in geometry or updates to the design, the process has to repeat itself. The analyst has to deal with importing the CAD again, to meshing, setting up the analysis, rerunning it. And at each phase of this, there's different challenges. So with each challenge, there's significant time spent. So it's honestly no wonder why most companies dedicate entire departments for simulation folks, since any sort of simulation is a very time-consuming task, which makes it hard to democratize and make accessible to other engineers who might be doing other tasks aside from analysis. So with all these considerations in mind, we need a workflow that empowers users to have rapid solutions, as well as something that allows cross-functional usage for designers and analysts alike to pick up. So one solution is the ability to solve problems quickly and boost simulation productivity. Probably the most time-consuming aspect of simulation is meshing and cleaning up the geometry. If we altogether eliminate the time spent meshing and cleaning up the geometry, we save a lot of time during the simulation process. Meshing can kind of be like a juggling act for analysts to balance effort with time and quality. Usually the analyst has to make some sort of engineering compromise in terms of accuracy versus speed when it comes to choosing which elements to use and whatnot. So an ideal solution would basically allow a tool to make those sort of meshing decisions automatic. Like I mentioned before, some aspects of CAD that designers don't necessarily care about, like part overlaps and gaps, as well as small features like surface edges that are really close together, these things can cause problems for meshing. So as an example, if we look at a screw with a thread, in the traditional FE sense, these threads would have to be removed from the modeling for meshing. We have to do this because in the traditional finite element sense, the size of our smallest elements generally determines the duration of the solve time. So a finite element model with really small elements like the threads on a screw would lead to very tiny sliver elements, so that would lead to longer solve times. Also, the elements on the thread of that screw would probably have poor quality, so we'd probably have poor results even if we did include them. So ideally, if we had a solution that allows us to import the CAD as is, even screws with threads without having to remove them, this would help reduce our pre-processing time. So in the previous slide, we talked about having a solution on the pre-processing side, meaning how can we reduce the effort needed by the user to clean up the CAD? But we didn't talk about the time involved during the solve process itself. So we can see in this chart that when we're doing a simulation study, not only does the effort involved with setting up the analysis increase as the assembly gets more complicated, but the time to solve actually increases as well. As I mentioned in the last slide, a part of this is due to the fact that more parts means more meshing and more geometry preparation. But another huge factor involves the number of equations the solver engine needs to solve. So a larger assembly usually has an exponentially larger number of equations for the solver to solve. So once you remove the amount of effort for both the user and the solver, the process for simulating goes much faster.
So the last point I wanted to make is that an idealized workflow enables simulation-driven design. So what do I mean by simulation-driven design? So as anyone who's ever worked in product design, we know that different engineering domains are siloed into different groups. We have designers who work on the CAD. We have the analysts who take the CAD and discretize it for finite element analysis to run simulation and give feedback. So what I want to address when it comes to simulation-driven design is that this feedback between the designer and analyst is very iterative, and it's also very inefficient. So when a designer sends a design and it gets analyzed, the FEA guy then makes a suggestion, which the CAD guy then incorporates and sends it back for validation. So an idealized workflow introduces simulation-driven design to include upfront simulation early in the design phase to make informed decisions. We want to introduce a workflow that supplements both the designer and the analyst. For the designer, having a powerful simulation tool that can quickly give accurate results for even large-scale assemblies is useful. And for the analyst, it can help with doing a quick design comparison that can later then be verified with the conventional FE process. So even for the analyst, we're not looking to replace the detailed FEA work that they may be doing with OptiStruct or any other solver, but we believe that having an upfront simulation tool to help sort through and evaluate design iterations has tremendous value. So now that we talked about the challenges in the electronics industry, let's kind of play out a typical scenario where utilizing rapid design evaluation would be helpful. So as an example, let's describe the life, a day in the life of two engineers. We have Kate, who is a design engineer, and John, who is responsible for the analysis. So John and Kate have been working the past few weeks on finalizing a design that passes structural certification. However, Kate just had a design review meeting with the supplier, and the supplier is unable to manufacture the proposed design, so she has a meeting with John. In this meeting, Kate has 5 different design variants that she thinks will meet the manufacturing specs, so she asked John if he can evaluate all 5 designs. So I can imagine John is internalizing some sort of scheduling in his head about how long this will take, so he asked the obvious question of when do you need this by? Of course, the classic answer in the consumer electronics industry is we need those results by today. So at this point, John knows he's probably pulling an all-nighter or working overtime to get those results to Kate to meet critical design review. So John has 5 design variants he needs to evaluate. So going back to this typical simulation workflow, he'll have to repeat this process 5 times of having to import the CAD, remesh, set up his analysis, and he knows his back is against the wall because he has a critical deadline he needs to hit. So with this in mind, let's show how we can approach this scenario with an idealized workflow where we introduce rapid design evaluation to help someone like John realistically achieve his deadline so that he can get results the same day. So let me go ahead and get to the demo portion of this webinar and show you how we would go about setting a baseline model for analysis and how rapid structural evaluation could give answers in minutes instead of hours. So in this model, or in this demo, we'll be looking at this game controller. We can see that we have buttons, we have the casing for the controller itself, and a trace that connects the buttons to the PCB. If we zoom in on the PCB, we can see the complexity of the model lies in the PCB, since the rest of the model is fairly simple, but the PCB is not. So to start this demo, again, we'll take a look at this model. And from the outside, it doesn't look too complicated, but if we zoom in on the PCB, we can see there's quite a number of parts on here. We not only have the board, but we have chips, we have a heat exchanger and USB connection and all that stuff. So if I query the amount of parts in here, we have about 242 parts, with the majority of those being on the PCB processor. So the first step in this analysis is I want to start applying materials. In this case, I've already applied the materials to the parts, but just to show you how you would do that, you would simply click on the part and go to a material database where you can customize your own materials and assign those parts. So if I open up my assembly tree, we can see the name of the materials right next to the name of the parts themselves. So that's how we know how these materials are being assigned. The next step is I want to look at my contacts. So there's automatic contact generation that's based off of a proximity and penetration tolerance. So if we just kind of quickly review our contacts, we can see that we have contacts defined. We have a large number of contacts. So if I do show all, I can look at the contact surfaces and the contact interactions between the various parts in my model. So now that the materials and contacts have been defined, I'm going to now define my boundary conditions and loads. So I'm going to go ahead and set up a linear static analysis. And to just start this analysis, I'm going to go ahead and apply a fixed constraint to this little middle stiffener. So I'm going to fix it in all degrees of freedom. The next step is I'm going to apply a pressure. So I'm going to apply a pressure to the ends of the controller, and I'm going to go ahead and assign 10 megapascals. So at this point, I'm just going to go ahead and run it, and you can see it solving in real time. So 10 megapascals might seem like a lot, but I've been playing a lot of Call of Duty lately, and there's a lot of people raging on the other end, and I wouldn't be surprised if people are just like smashing their controllers and Hulk smashing things and kicking their TVs and whatnot. So we see that this analysis only took 16 seconds. And again, we did this in real time with no sort of geometry cleanup or meshing involved. Normally something like this in traditional FEA, we'd have to defeature things like the copper wires because that might lead to longer solve times. So as we're post-processing here, we can see things like the local deformation, like the peak deformations, and we can also look at the peak von Mises stresses. And at this point, we're just going to go ahead and start setting up our other load cases. So the next type of load case I want to set up is a normal modes analysis. So for this normal modes analysis, I'm just going to request the first 9 modes, and I'm going to apply the same constraint to that middle stiffener. And again, we're going to solve this in real time. So as we see this solving, we should get our results in a matter of seconds as opposed to minutes. And so if we look at how long that took 21 seconds. So when we post-process this, we can look at the natural frequencies. So we can see our first natural frequency as well as the accompanying mode shape for that natural frequency. So if we just kind of go through this list, we can see the different mode shapes as well as the different natural frequencies for each one of those mode shapes. So we see the twisting, we see the bending that happens for these different mode shapes. Another analysis I now want to do is a thermal analysis. So I'm going to go ahead and apply an operating temperature of 60 degrees Celsius to the board and set up our convective heat transfer coefficient to basically simulate a steady state temperature. So I'm going to first apply that operating temperature of the board to the face of the board. The next step is I'm going to now choose these heat exchangers and basically say there's an ambient temperature of 35 degrees Celsius that kind of represents the air around it, as well as a convective heat transfer coefficient of 200. And we'll just go ahead and run this. So again, once we run this, this analysis finishes in a matter of seconds as opposed to minutes or even hours. And we're able to plot our temperature distribution on the board and the heat exchanger. So the next step is I want to now couple these temperatures to a thermal stress analysis so that we can get the stresses and displacements from the contraction and expansion of the thermal load. So in the setup, I can just go ahead and map the thermal loads from my thermal analysis. So if I go to this thermal loads tool, I can just go ahead and link the thermal loads from my thermal analysis to this linear static analysis and run this. And again, we're doing this in real time, so we can see that this solves really fast. And once this finishes solving, we can then post-process this to look at the stresses and results for the contraction and expansion, and we see this solved in 12 seconds. So if we post-process this, we can now see the deformations from the contraction and expansion as well as the stresses. So now that we set up our baseline model with several different load cases, what happens when we're asked to evaluate different design variants? So like in John's case above, he had already set up a model prior to case changes. So in the classic finite element sense, he'd have to delete his old mesh and bring in the new CAD and remesh it. But in this demo, we're going to show the strength of our workflow where there is no longer a need to tediously go through iterations. We can simply import our new CAD and have it nicely set up for analysis. So in this demo, I'm just going to go ahead and set up our new assembly. So I'm just going to go ahead and import our new assembly that our designer just came up with. And so we're going to import that directly into the session. So as this is importing, we see that it finishes importing, and we can see that our session automatically populates the same 4 load cases that we had set up before with the linear static analysis, the modal analysis, and the thermal coupled analysis. So I can quickly compare these two assemblies. So if I just click on one assembly, I can see that it has 275 parts. So if I query the previous assembly, we can see that our previous assembly has 242 parts. So we've introduced at least 30 new parts on top of any parts that may have changed in geometry. So we're able to just kind of toggle between these two assemblies rapidly within the same session. So if I expand my material tree out, I can see that we have our different parts, and we can see that some of these parts don't have material names next to it. So we can go ahead and assign materials to it. The next thing is I want to evaluate our contact conditions. So I just quickly checked if there were any disconnected bodies. Next, I just want to visually inspect these two assemblies. So if I just kind of toggle between these two assemblies, we can see that we added a port next to the USB port, and we also increased our heat exchanger. So we added a heat exchanger as well, and the chip layouts have also changed. So now that we've established our assembly has changed from one design to the next, let's look at the contacts. So as I mentioned before, contacts are kind of automatically set up. So we see that our contacts have already been automatically generated, and we even see this flag telling us that the contacts have changed. So you can just quickly review your contacts and see where they've changed. And again, they've set up our analysis already for us, like by automatically importing this assembly. We can see that these load cases are automatically set up, and we can just simply hit run, and we're able to look at the results for each one of our load cases without having to reapply the loads and reapply those load case setups. So everything is nicely set up for us. We just simply had to import our geometry, our new assembly, and it's able to not only tell us the differences, but it sets up our new types of load cases for us automatically without us having to reset those up. And again, we see that as we systematically go through each one of these load cases and we hit run, we see that these things solve very quickly again. So we're rapidly evaluating these different design changes in a matter of minutes rather than hours. So we could repeat this process 5 times for 5 different assemblies, and we'd have, we'd be able to set them up rapidly the same way. So to summarize what we've discussed so far, we described the main challenges of the consumer electronics industry, namely that the time to market makes deadlines incredibly competitive, and the sheer number of parts that many electronics assemblies have. So we took a part that had 242 parts and also another assembly that had 275 parts. And normally a process like that would take hours to solve, but we solved that in a matter of minutes. The takeaway here is that we generated a solution that addresses the issue of the complexity of these assemblies, and we were able to generate a quick answer. So we introduced a workflow where we not only didn't have to set up any mesh or clean up the geometry, but we were able to rapidly introduce design variants and have the tool readily set up the load cases and flag us about any design changes and solve those load cases at an extremely fast pace. Not only that, the GUI, the workflow was incredibly intuitive. There wasn't really any sort of cleanup or meshing, again, that we had to do on our end. It was simply a matter of importing an assembly, a design, applying loads, applying constraints, and hitting run. So if we go back to John's scenario, where he was asked to evaluate 5 different design variants in the same day, using the workflow we just showed, we were able to realistically cut that time down from a matter of maybe an entire day's worth of work to just a few minutes, since we avoided the whole iterative cycle of having to change the boundary conditions and mesh for each update in CAD. So we've essentially introduced a workflow that empowers an analyst like John to meet the rapid decision-making required in the electronics industry. Furthermore, this workflow empowers a designer like Kate to not only have to not rely on an analyst like John, but she's able to make her own design decisions and allow John to focus on his detailed FEA analysis so that she's able to narrow down her own design variants. That way, John can just focus on the validation aspect of the design and do more complex types of analysis. So the simulation-driven design workflow allows both engineers the ability to eliminate guesswork and make engineering-based design decisions to cut down on this iterative design cycle between designing and analyzing. With that being said, let's just open this time up now for any questions.
Thank you, Leo. Very interesting. There are a few questions already here. I invite our attendees to post more questions. We would love to answer them all. We'll pick one of the first questions we have here is, what load cases can you support with this simulation process?
Yeah, so we pretty much support any, pretty much support all linear static and nonlinear quasi-static types of load case with this workflow. So as we can see in this slide, we do the conventional linear static stuff, but we can also do nonlinear, so like geometric nonlinearity contacts, like sliding contacts, sliding with friction, etc., as well as material nonlinearity.
Okay, so this is answering some of the next question, which was, is there a material database and can we do nonlinear materials?
Yeah, so there is a material database that comes with the tool, but you're also allowed to define your own materials and to add like material nonlinearity, so material in the plastic region, behavior in the plastic region as well.
Thank you, Leo. Another question here is, Stip says, you mentioned that connections are done automatically. What type of contacts or connections can be taken care of?
Yeah, so most of the contacts are bonded by default, but we can also change those to sliding and separation. So we can, yeah, you can essentially define sliding contact and separation as well. Thank you, Leo.
I think we covered most of the questions we have here, or all of the questions. Okay. I invite everyone to keep sending us their questions, and we're more than happy to answer them.
Okay, let me move on to the next portion of our presentation. So in the previous section, we talked about how rapidly evaluating design can help save time, but what if we wanted to update the design ourselves and observe the effects in real time? So again, recalling the scenario between John and Kate, let's say John realizes that none of the 5 design variants that Kate proposed pass his structural evaluation check. So he needs to update the CAD design itself. So let's go ahead and show this demo. So let's go ahead and take the updated version of the game controller we analyzed and assume this is the final design variation that has the added port and the extended heat exchanger. So in this demo, I'm going to go ahead and go to my preferences and use the SimSolid solver. So that's the same engine we were using before to quickly solve the assembly to get the fast answers. So again, once we hit solve, we see this run in real time and we get our linear static results in a matter of seconds as opposed to minutes or even hours. So now that that's done, we post-process these results. And just to clarify, this was run with the same pressure of 10 megapascals on the side and the fixed constraint on that middle stiffener. We can then observe the peak displacements and the peak stresses as well. So once we animate this, we can see that it's the same behavior and our peak stress values match what we saw earlier. So if we look at the stress, we see that it's about 4,000 megapascals at the corner of that PCB processor, which is past the yield limit for the silicon material that we used. So as an analyst, when I'm looking at this, I know that I need to stiffen up my design. So the first step that I'm going to do is that I want to basically make these stiffeners much thicker. So if I use the tools here, I can go ahead and modify the CAD design itself within the tool. So I'm just going to go ahead and click on these stiffeners. So I clicked on that bottom stiffener as well as the middle stiffener, and I just made them a lot thicker. So once I made those design changes, I know that my design is now stiffer. So in theory, my stresses should be reduced. So to quickly evaluate the structure now, I'm just going to go ahead and go back to analyze. And again, we're running this really fast in real time. So as this is solving, just some things that we're kind of noticing here is that, yeah, there's a couple of design changes that we can make. So as we finish solving, we can now see that our stress has now been reduced from 4,000 plus megapascals to 3,000 megapascals, and that's because we basically bumped up the thicknesses of our stiffeners. So we can kind of toggle between the two results, and we can also hit this little compare results button to quickly sort of view the stresses between both designs. So I can just toggle between my baseline, which had the thinner stiffeners, and the second design, which had the thicker stiffeners. So if I go back to this design, I can do a couple other things here to help with that stress concentration. I can add fillets. So if I click on the fillet tool, I can click on an edge and add a fillet to that control board. So that would, in theory, help with some of the stress concentrations. If I wanted to move some of these bolt hole locations, I could just go ahead and click this move face tool. And that way I can just click on these bolt holes and just move them. So if I wanted to change any one of my mounting locations for the PCB board, I can just quickly click on some of these features and simply drag them and move them about in different places. So this demo was just an example of how we can basically take a design, rapidly evaluate that design, and make our own engineering judgment to make design changes on the fly and generate those results quickly. But what if we wanted the tool itself to be able to generate a design? So to preface this, I want to talk about the different generative design tools and optimization capabilities we have within the same platform. So one such tool is topology optimization. So topology optimization is basically material removal and redistribution. The topology optimization tool basically uses the solver in the background to basically retain material where the majority of the strain energy is, so that it's a load path dependent design generation. So basically, you're going to get a design generation that lies along the load path of the applied load. Another type of optimization method we can use is topography optimization, which is basically taking things like a stamped sheet metal part and being able to generate stiffeners for it. I've also seen very interesting ways that people have used this optimization technology. An example being a beverage company wanted to optimize the number of grooves on their bottle. So if you have too many grooves on a bottle, then that bottle's kind of prone to buckling if you're stacking it. But you need the grooves there to stiffen the bottle so that when you're gripping the bottle, fluid doesn't come out. So they use topography optimization to basically optimize the number of grooves and the pattern of the grooves to meet their engineering objectives. Another type of optimization we can do within the same platform is something called shape optimization. Basically, we're able to locally manipulate the shape of our designs to basically reduce things out like stress concentrations. And lastly, something called size optimization is basically parametric optimization. So anything that's a parametric value like thickness or beam cross-sectional area, anything like that. Again, anything that's a parametric value in the finite element sense can be optimized for. So these two different tools kind of comprise our design generation capabilities within this platform. Topology and topography constitute our concept level design tools where we're able to make drastic design changes, whereas shape optimization and parametric size optimization allow us to do design fine-tuning where the design is already pretty much locked in, but we're just tuning a few parameters here and there. So the folks behind our optimization capabilities were smart enough to know that it's not enough to just generate a concept. The optimization generation has to be grounded in manufacturing feasibility. Hence, we were able to sort of come up with the concept of manufacturing constraints. Some of the manufacturing constraints that we have are the ability to control the member size, being able to enforce extrusion or draw direction constraints to ensure that there's no cavities in the design generation. Also, if you're doing any sort of additive manufacturing, you can apply overhang constraints, so that ensures the design generation concept doesn't exceed some sort of overhang angle. If you're limited to stamped parts, we can basically apply a constraint to enforce the thickness to be uniform and to ensure that there's no holes or cavities throughout the part. So let me just show another demo of design generation. So let me just take the same controller we had before. And again, we're going to apply the loads on the end of the controllers pushing up and having the fixed constraint in the middle. But we want the tool to inform us of how to generate a stiffener design. So again, taking the same model, we know that we already have an existing stiffener sort of at the base here. And maybe that's not the optimal place to place a stiffener. Let's let the design tool come up with a different design for how we should place our stiffeners. So the first thing I want to do is I want to increase our design space to basically give the optimization tool more room to work with. So I basically extruded the base plate to meet the same height as the stiffener, and I also took out the holes that came with that. The next step is I now want to basically isolate the back plate because we still need this controller to have a back plate. So I basically want to retain that back plate feature. I'm just adding stiffeners to the back plate. So I'm just going to go ahead and cut my model, and I basically want to keep that back plate. What I'm doing here now is I'm basically sort of cutting out the PCB controller space. So I'm essentially making that space an untouchable area to basically say I don't want any material in this area. Like, we want to leave that space open for our PCB. So finally, now that we've had our models sort of set up for this design space, I now want to select that middle part that I just extruded and make that my design space. So in essence, we're going to basically run an analysis on this, a baseline analysis, just to see what the baseline sort of benchmark is. And this is an overly stiff design because we've filled up our entire backspace area to have a thickness basically to the height of the controller. So we're going to set up an optimization later, but we're going to first run this baseline design to see what our results are. And this is going to be an overly conservative design. And again, the concept or the objective of what we're trying to do here is we're trying to achieve some sort of stiffener pattern, like basically what makes sense as a stiffener concept, and have the tool inform us of where to place stiffeners. So here's the results for our baseline analysis. And again, this is the overly conservative design, so we can see our different stress and deformation here. My optimization setup is going to be to maximize the stiffness, and I'm going to set a constraint to basically reduce 70% of the pre-existing material of where that design space is. So basically, again, I'm telling the tool I want to maximize my stiffness, but I want to remove as much material out of this design space as possible. And I did that with an extrusion constraint. So basically, that's ensuring that whatever design concept is generated is extrudable. And if I kind of rewind back here a little bit, we can see that we get this stiffener concept. So this stiffener concept is not altogether useful because we already had this sort of back stiffener here, but it is telling us to place another stiffener here to help with our engineering objectives. So that seems like an interesting concept, but it's not interesting enough to me. So I'm going to change my optimization setup and take out that extrusion constraint. And this time I'm going to apply what we call a symmetry constraint. So basically, I want my optimized pattern to be symmetric about two planes. So I'm going to have it symmetric about these two kind of red planes, and I'm going to set the same engineering objectives. So here, as I'm running this, once this finish is running, let's go ahead and look at our results. So once this is finished running, if we look at these results, we can see that our concept, if we kind of zoom in here, we can see that the concept kind of creates these cavities and creates kind of a top face of our controller, which is feasible manufacturing-wise because we do want a top face on our controller. And if we kind of isolate out this design, we can see that the shape kind of follows like an I-beam, right? So I think this is an interesting concept because it's a classic case of the optimizing tool giving us a design generation concept that's grounded in real-life physics and reality. We can see that this design is essentially an I-beam. And we know that this makes a lot of engineering sense because the type of analysis we're running has a lot of bending to it. So we know that in a bending cantilever beam, for example, an I-beam is probably the best type of design to address those bending stresses. So in this design generation, it did give us an I-beam without us telling us to make it that shape. We basically just said, here's a design space, come up with the best design possible to achieve that engineering objective. So we were able to do that. And right now we're just basically wrapping a geometry around this optimized shape. And at this point, we can export this optimized shape as a parasolid, a step file, whatever. So we're able to take a design generation and export geometry from it. So just some key takeaways from that sort of section. What we discussed here was we see the value in using simulation-driven design to include simulation upfront in the design. So that way we come up with the right design as early as possible. Again, we empower both the user, who may be a designer or an analyst, to analyze, diagnose, and optimize. The designer doesn't have to rely on the analyst. The analyst is able to provide quick design choices to the designers. And we can also see the capabilities of being able to make real-time updates within the tool to modify the design, as well as to have the tool itself generate a design that's grounded in engineering-based physics. So with that being said, let's open up this time for questions.
Thank you, Leo. Very interesting second part of this presentation. And they definitely triggered some question here from our audience. So please let me read here. One of the question is, what kinds of optimizations are possible and what engineering objectives can an engineer target?
Yeah, so in the previous slide, kind of we showed like the various different optimization methods. So we're able to do not only material removal and redistribution, but we can kind of manipulate material. We can also change parametric values of our sort of problem setup. So any one of these things are part of the optimization capabilities that we can do. So the other question was, what are some of the objectives we could do? In our demo, we did a maximize stiffness and reduce mass type of optimization setup, but we can also do things like try to achieve a certain stress value while reducing the mass. We can also target things like natural frequencies. There's a large number of things, and any one of those can be sort of a webinar in of itself. But basically, you have all sorts of optimization capabilities within this tool.
Okay, thank you. The next question is, can I generate CAD from the optimized designs? Yeah, so I may have gone a little bit fast towards the end of that demo, but basically we were able to take that optimized design and simply wrap what we call a polynerb shape around that design. So a polynerb shape is basically a CAD-ready sort of geometry. We're able to just basically wrap CAD around our optimized shape and export that as any sort of neutral geometry format. So step, parasolid, etc. I have some more questions coming here. Next one is, can we generate a finite element model from the setup you have shown?
Yeah, so since this is all running finite element technology behind the scenes, like this is not like some sort of random one-off tool. We're actually using finite element behind the scenes. We're just doing it a lot quicker, and we're enabling smart methods in the background to give you optimized design. So it is still running finite elements, so we're able to export a finite element deck behind the scenes, so you can load that into your HyperMeshes and other preprocessors that you would feel comfortable using.
Okay. I see one more question here, and I think we have the time, is how accurate are the simulation methods you have shown?
Yeah, so so this is basically running our solver technology behind the scenes. So the optimization portion of it is OptiStruct. So OptiStruct is a commercially validated solver that companies like Boeing, GM, Ford have been using for years. So that's definitely a validated code. The earlier part of this demo was using the solver called SimSolid. So SimSolid is part of that rapid design evaluation physics stuff. And we stand by that technology as well. We've written white papers on it. Kind of a slide I want to show is that we've done our own internal benchmarks on this tool, comparing it to like hand calcs and other finite element codes. And a third-party company, or not company, but organization, NAFEMS, has also benchmarked this tool and written an article on it. So we do stand by the accuracy of this tool, and it's even been validated by a third-party organization. So we're happy to send this article as well as our white paper and validation manual to anyone who's curious about it.
Thank you, Leo.
Sure.
I'm scrolling up and down here, making sure that I covered all the questions. We have a little bit more time if anyone else wants to ask additional questions. Not getting anything here. Probably, Leo, I don't know if you have any additional content or topics that you would like to share with us before the end of the webinar.
Yeah, I just want to summarize this thing, and I guess that'll wrap us up. So yeah, in conclusion, in this webinar, we introduced a workflow that supplements both the designer and the analyst. And this workflow is meant to address sort of the difficulties and hurdles of the consumer electronics industry, namely the amount of parts and sort of the time to market and the sheer number of parts that a lot of electronics assemblies have. So this workflow empowers both the designer and the analyst. So we're basically enabling the designers to have access to a powerful simulation tool that can give accurate results and to give those results very quickly. This workflow also empowers the analyst, someone like John, who might encounter situations where we have a lot of last-minute design evaluations where they might be asked to evaluate 7 different design variations within the same day. So this workflow not only helps to rapidly evaluate those designs, but it helps to get to the right answers quickly. So we see that it's not just about generating fast results, but it's about generating informed results as well. We're able to manipulate the geometry in real time within the same tool to get our results. And we're able to also ask the tool to give us the right design. And that's based off of engineering physics. In the demo we saw earlier, we saw that controller as it was bending. The design generation that it gave us was an I-beam concept. And that's pretty much grounded in real life because, again, we know that in real life, an I-beam is like the optimal design for a part in bending. So we're able to see that a tool like this is able to give informed decisions to help take a lot of the guesswork and a lot of the tribal knowledge that would go into product design out of the equation and empower both designers and analysts to have access to a lot of smart decision making and to basically cut down on that time. So yeah, that about wraps up my presentation. Thank you for attending. My contact info is on this slide, so if anyone has any sort of follow-up questions or any interest in knowing more about these tools, feel free to reach out to myself or the email link